Hi, my name is Roger, and I'm going to be walking you through a number of machine learning architectures, starting with the transformer. And the idea is to give you an intuitive guide to understand how these architectures work. When the transformer architecture was first introduced, it led to breakthroughs in language translation, and soon after, many people applied the transformers to other fields such as computer vision, science, protein folding, reinforcement learning, and generated similar breakthroughs. So how does the transformer work? We'll go piece by piece, breaking down the different components. At a high level, you have your encoder that takes in inputs and then passes it onto the decoder, and the decoder generates outputs word by word. And we'll go through embeddings, positional encoding, the encoder, the decoder, and linear and softmax layers. So what's an embedding? An embedding converts words into hundreds of numbers, and these combination of numbers allow us to group words that are related for almost any reason. And so now we can understand the meaning behind words and how they relate to each other in many different dimensions. For example, in our chart here, we have maybe two of these numbers, and we plot all our different words, in this case, cat, dog, whale, elephants, and then we can group them based on similar attributes that the computer kind of determines on its own. So embeddings convert words into numbers and meaning. Positional encoding. One important thing we want to do is keep track of when a word appears in a sentence. And one way to keep track of that position is to add something based on the value or based on the position to that word's value. So in this very simple example, the words that come further along in the sentence are larger. What do encoders do? Encoders add more meaning to words, and they do that by doing some math over and over again. And we'll go deeper into what that math is, but at a high level, it references other words in the input and then uses its internal understanding of the data it was trained on to provide an encoded meaning of the words. To sum it up, an encoder represents the meaning of the sentence based on the embeddings and the encoding. So we'll go deeper into the encoder, starting with the multi-head attention and then the add norm layers and the feed forward layers. What is attention? Attention is what calculates how much each word cares about each other word in the sentence. How we do that is we use a query key value method. So you can think of Google. If you send Google a phrase, your phrase is then understood and then it looks into the database using keys and then returns values. So we do something similar. The model has trained a bunch of questions or a query. We can use this query to ask all the other words in the sentence, hey, what do you mean to my word? And you get a score. And then based on that score, we augment our word, our current word, with a percentage of the value from these other words. So all the other words are slightly augmenting the value of our current word to keep track of the attention that we want for each other word. And we do that for every word. And multi-head attention is just having multiple query, key, and value matrices. So this allows for more information to be encoded and performs better than just having one large key query value method. And then these linear and concat layers help split and merge things back together. After our attention layer, we have our add and norm layers. We continue forward by adding the original input in with our output and then normalize the result. So adding the original input, make sure that the original input isn't entirely overwritten. It allows our model to keep track of like the ground truth. And then normalizing makes training easier and more stable. Next, we have our feed forward layers. And these are standard ways to organize neural networks. It combines linear and nonlinear equations to save complex patterns and relationships. So you can note that these layers don't use any of the input data, so it helps also ground the model. You can think of it as additional processing. Multi-head attention allows us to calculate meaning using the embedding and position of different words. Our add and norm layer maintains information about the input and also adds stability when we're training. And then our feed forward adds more complexity. And then next we'll go on to our decoder. So how decoders work is it generates a response by passing the previous word back in for context. And so if you look at the diagram that I drew, you can start with the start block. And as it goes through, the decoder determines that I is the next word. You pass an I back into the decoder, and then it determines that am is the next word. You pass in I am, you get A, and you can pass in I am A, and then you get student. And also something to note, within these generations, the decoder uses the output from the encoder to hone in on what it thinks is the best response. So that's why we need to do the so our decoder generates output word by word. What's masked multi-head attention? So if you remember in the beginning, we had our attention mechanism. It calculated how it related words to each other, all the words in the sentence. In our case, in the decoder, we don't want words that later to influence the words that appear before. So we want to basically zero those out while we are calculating attention for the first word in the output. And so by doing this, it allows us to train a model that's better at predicting. So it can't already know what's going to happen. Our masked multi-head attention practices generating the word by hiding knowledge about words that come after. One thing that's different from encoders and decoders is that the decoder uses the output from the encoder to attend to all the positions in the input sequence. So that means the decoder has knowledge of what was asked when we are decoding. To summarize, passing encoded results to the multi-head attention layer gives attention to the input when generating. Our final two layers determines what word we output, our linear and softmax layers. And our linear layer maps the decoded results into a list of scores. And then the softmax layers then turns these scores into probabilities, and the highest one is chosen as the next word. And that's the last part of our decoder, the linear and softmax layer. Again, to summarize, the encoder distills the meaning of our input. And then we want to pass that distilled meaning of the input into our decoder. And so next, we're only looking at our decoder, and we generate word by word and using the output to also generate the next word. And there's a little bit of a difference between the encoder and the decoder. We use a masked method, so it can train to be a better predictor versus being something that's all seen. And in our multi-head attention layer, we have our specialized encoder key and value matrices. And so I hope that helped. I'll add links in the description to follow up. If you wanted to look at the original paper, this really good illustrated guide to the transformer, and Andre Karpathy's really great introduction to transformers that gives you like the back history of how the transformer was. Thanks, and I hope you like and subscribe.